8.4, this simplest problem. Oh, hey, why one left? Yeah, all right. Yeah. So the current equation, A coefficient, B coefficient, they are constant, the simplest. Okay, all right. Yeah. Yeah. Solution. Yeah. How to solve it. Yeah. Here you can see, although we had a lot of discussion, but our discussion still not enough to help us solve this problem. So we need to find some special way to solve it. Here, to get idea, insight in structure. We want to get some insight for the structure of the solution. Here, so you can see something. Right? Yeah. But insight, to get insight from our old experience. Our old experience. First order ODE. That's our old experience, right? Yeah. So let's consider. We try to get inspiration from our first order solution experience. Yeah. So let me bring up. Let's consider first order solution. You're familiar with this solution, right? First order, okay? The solution form. Yeah. So we can write a general solution for this equation. The general solution is y equals c times e to the negative kx. Yeah. We want to get inspiration from this solution. Yeah. C not important, right? In a constant. Because here we just want to get one special solution. So C is not important. Yeah. So we remove that C. Yeah. Second, K we do not know K, right? Yeah. So that K unknown. Yeah. Yeah. But the structure we want to keep. Okay? Yeah. So we don't know K. So we just want to put a parameter there. Certain parameter in the position of K. So we want to try this structure, y equals e to the lambda x structure. Yeah. Yeah. Because we want to take the, appropriate structure. Yeah. In this kind of thinking, yeah. We want to get appropriate structure. We want to get insight. We want to get some inspiration from our old experience. Yeah. Here we get it. Y equals e to the lambda x. That's what we learned from our old experience. Now we want to try. Okay. Here you can see without old experience, it's not easy, right? How can you guess this structure, right? Without old experience, it's hard to guess this structure. Yeah. So that's why our old experience is important. Yeah. All right. Well, now we try this structure. We plug in to the given equation. Let's take the first derivative, yeah, lambda to be determined. Yeah, later we will see what should be the appropriate lambda values. Yeah, we will see that. Yeah. All right. Y prime equals lambda times e to the lambda x. Yeah. So lambda multiply the original function. Yeah. Y double prime, y lambda squared times original e function. Yeah, pretty simple. Yeah, the structure very friendly. Yeah, so let's put it back. Yeah. Plugging back to the given equation, and we can factor common factor e out. So inside parenthesis, we get an algebraic equation. Lambda squared plus a lambda plus b, it's an algebraic equation. Okay? So you can see the new equation, no differential, no derivative in the new equation. It's an algebraic equation. Yeah. We also know the e term can never be 0, right? Yeah. E to any number cannot be 0. So E term, we can cancel out. We can, remove it. We can remove it. E term, E function term. So we convert a differential equation to the algebraic equation. We call this new equation characteristic equation of the given differential equation. Characteristic equation. Okay? Yeah. And the lambda can be solved from this quadratic equation. We know how to solve it. Yeah. Lambda values. Yeah. Or also called auxiliary equation. Yeah. Let's use the quadratic formula to write lambda expressions. Yeah. Lambda 1 by that standard quadratic formula. Yeah. Lambda 2, just the minus, okay, the sign, the difference. Yeah. Yeah. Then, with lambda values, 2 possible values, 1, 2, now we need to write out the final solutions. But for the final solutions, we know inside the square root, sometimes it's positive, sometimes 0, sometimes negative. There are 3 cases we need to consider inside the square root. Yeah. All right, the first case, it's the simplest case. Yeah. 2 distinct real roots for this quadratic equation if the part inside the square root, a squared minus 4b, is positive. Yeah. 2 different real roots. Yeah. So that's the simplest case. Yeah. Here we assume in the first case, what are the 2 solutions? Can you give me quickly what are the 2 solutions? Y1 replace lambda by lambda 1, right? Y2 replace lambda by Y2. That's it. That's all you need, right? That's simple. Okay? All right. Yeah. Then, for the second case, a real double root. Yeah. Double root. 1 root repeated twice. So we call it double root. Yeah. That means the equation is, we can write the equation as the double root form. Yeah. So let me show you the double root form. Yeah. Because double root, single root, we should not treat them the same thing, different thing. The properties would be different. So here I want to emphasize this double root difference. Yeah. Let me change the color. All right. Double root case. Double root, your variable is lambda minus its root y0, let's say, square equals 0. Okay? Yeah. Square. When we do factor decomposition of the left-hand side, we get this representation, lambda minus lambda 0 parenthesis square, so we call it double roots. Double root. Yeah. The property is different. Yeah. The graph is different. Okay? The graph is different. So do not treat as, so some of you may treat, because we can take square root both sides, so we get a single root, y minus y0. Yeah. Then you change the property. Yeah. If you do that, although you get the same lambda equals y0, but you change some property, so that could affect some later other expressions. Yeah. So we should preserve this property, original property, double root property. Okay? All right. So for the double root, now, what's the possible solution? We go back to it. Yeah. Y0, we can find Y0 because the square root term is gone, right? Square root term is gone. So when you consider the double root case, so you get lambda 0 equals negative 1/2 times A. Okay? That's Y0. Only one root. This root repeated twice. Okay? Multiple roots. Yeah. That form, but we only have one value, Y0. Yeah. So your first solution is e to the Y0 times x. But question, what's the second solution? Because this is a first order differential equation, we expect to get a second solution. Second, essentially different solution. The solution must be essentially different. Okay? But we cannot see it, right? We cannot see it. Yeah. For the first case, lambda 1, lambda, we can see two different solutions immediately. But for this second case, we can only see one easily. But how to see the second one? It's hard, right? Yeah. Do you have any idea to tell me the second one? Try to, discover it. Here we have the first one. How to get a second one? Anything we can do to get a second one? What do we learn in the first half? What do we just learn in the first half before the break?
The substitution.
What's the name of the technique? There is a name for this whole technique. Yes, reduction by order. Can you apply that reduction by order to find the second solution? Yeah, we have the first solution. You have the first solution. Yeah. Here it's easy to get it. Yeah. Can you use that substitution you just mentioned, right? Yeah. Y2 equals U times Y1. Yeah. Here Y1. Then do all the things second. Yeah. You can do it that way. All right? Yeah. There is some way to do it. Some method. We can do it. We bring back the formula, we can find that. Okay? All right? That's the method. Yeah. All right. So I do not do it here. Yeah. But we will see later. Yeah. All right. So that's for this case. Case number 3, two complex roots if a squared minus 4b less than 0. Yeah. So, what is the special term for this expression? So do you remember? So when we do, any special term for it? Anyone remember? What do we call this a squared minus 4b? Here we check, compare with 0. Right. Any special terminology? What I mean is, math terminology. Any? Is it called discriminant? Discriminant? Anyone? Seems. Yeah. Yeah. Some term. Yeah. Yeah. Our textbook mentioned that. Yeah. Discriminant. Yeah. I'll double check. Yeah. Double check it. Okay. Yeah. Yeah. Not determinant. Discriminant. Yeah. All right. All right. Yeah. So here, two complex roots. If this discriminant, let me, if it's wrong, next time I will correct it. Yeah. Less than 0. Okay? All right. Two complex roots. Do you feel comfortable dealing with complex roots, complex numbers? I want to see, complex roots. square root of -1. Do you feel it's okay to feel comfortable with the number? Yeah, so this special notation, I equals root of -1. Square root of -1. It's not garbage. It is very important. This number is extremely important. Don't throw away. All right? Don't throw away. Yeah. So here, we need to use imaginary numbers, complex numbers, containing the imaginary part. A complex number has two components. Real part, imaginary part. Adding together, so we get a complex number. Yeah. Here, lambda, this case, there are two complex roots. Yeah. Don't throw away. If you throw away, you cannot find two solutions. Yeah. So keep it. And we will find two solutions, and you will see in the two solutions, the complex symbol will be gone. Okay? The complex symbol will be gone. Yeah. We can get around. Yeah. At the end, we can get around complex symbol I. That little I. Gone. But in our derivation, we need a complex number. Okay? Yeah. So that's important. Yeah. So for this class, not a big part, there is a small part. We need to rely on the complex numbers. Okay. Small part. Yeah. Complex numbers. Yeah. All right. Yeah. That's the third case. Next, we need to write solutions for all these three cases. Yeah. First case, we already have it. Yeah, that's easy. But we need to write out second case solutions and the third case solutions, especially the complex case solutions. All right. The first case, second case, third case. All right. And y1, y2, so we put it here. We need to use it to write our solutions. Yeah. All right. First solution, straightforward. Yeah. From previous slide, we already have it. Now we need to do the second case. Yeah. Double root. Yeah. All right. The second case, y equals this -a/2. This gives us the first root easily, but we need to find y2. It's not that obvious. Yeah. We may need to apply reduction by order technique to find it. Yeah. Yeah. Here, I want to save some time. Yeah. Otherwise, I need about 10 minutes to find it. Yeah. If I apply reduction by order, I need 10 minutes to find the answer. Okay? Here, I just give you the answer. Yeah. y2 equals x times this function. There is a little x time it. Quite natural, right? Yeah? We multiply that function by x. Okay? You can verify it. If you like, you can verify it. Plug in, derivative, second derivative, check, if both sides the same. That will be easier than reduction by order technique. Okay? Yeah. All right. Yeah. That's the case 2 solution. All right. Pretty good. Yeah. We like it. Yeah. All right. Case 3, complex. This time, we need to work on complex numbers. Yeah. Complex numbers. Okay? Yeah. Do not get scared. Yeah. Yeah. It's important. Yeah. Especially for you future engineers, it's important. Okay? Yeah. Complex number. Powerful tools solving engineering problem. Complex number. Yeah. Our textbook has some chapters about complex numbers. Yeah, but I look at the syllabus from last semester. It's not covered. Yeah. So we don't have time to cover that. Okay? Yeah, so in this class, so we won't cover those chapters about complex numbers. Okay? All right. Now, for case number 3, we write I1 equals this little I. Okay? Root of -1. Yeah. Here we have to use it. We cannot avoid it. Okay? Write it explicitly. I times root of b minus 1/4 of a squared. Yeah. Y2, the conjugate root. Yeah. Yeah. So we call it conjugate root. Yeah. 2 complex conjugate roots here. Yeah. But this big square root, it's not very convenient to write it everywhere, right? Because we need to write the formula many different places. So we want a simple symbol to represent it. So we introduce a new symbol called omega. Okay? Omega to represent this whole square root thing. Yeah. Omega, okay? Plus minus. Yeah. All right. So now this case 3, we use the notation omega equals the root of this expression. It's greater than 0. Okay? Then our expression could be simpler. Yeah. Now we want to write our 2 solutions. Yeah. All right. The first solution, that e part, then cosine omega x. Cosine. Why cosine? Interesting. For the complex case, we use cosine. All right? That's the first solution. Second, we use sine. Is it interesting? Yeah. We know cosine, sine, good functions, right? Very good functions, sine, cosine. Okay? Yeah. Here, when we see complex roots, we use sine, cosine. Let me explain. Yeah, because nobody can guess in that way, right? Nobody can guess like that. Yeah, so let me explain why it is correct. Yeah. All right. Euler formula. Anyone heard of this special Euler formula? Very famous. E to the I omega equals cosine omega plus I sine omega. This is one of the most important formulas in math. Okay. Fundamental. Yeah. Yeah. Our textbook has a proof using the series. Yeah. Expand E function as a series, then cosine function series, sine function series. Now you compare. Yeah. That's the way our textbook try to convince you this formula is correct. Okay? Yeah. Series. Maclaurin series. Okay? Using Maclaurin series. Yeah. I do not do here. Okay? So if you want to read, you can read that part. Proof. Okay? Small proof. Maclaurin series. All right? Here we apply this formula, Euler formula. Okay? Yeah. Because first we can write 2 solutions with complex numbers. Yeah. The first solution, here I use star version because that one I use complex numbers. Yeah. Here there is some C. Yeah. So this E part, I replace it by some C. Yeah, because that E part, we just keep it. Okay? We do not touch that E part. Okay? We copy key part everywhere. So here I keep that as a C. Okay? Yeah. To make it as simple as possible. Yeah. This corresponds to that E part. Okay? All right. Y2 star minus omega. Conjugate. Okay? Yeah. So these 2, they are also solutions, but they are complex expressions. Yeah. So we want to use real expressions, not complex expressions, right? real expressions. So we want to get rid of the I symbol representation. Get rid of it. Yeah. But in a a reasonable way. Not that you just take it away. You cannot take it away. Okay? Yeah. It's wrong. Yeah. All right. So let me show you. We apply Euler's formula to get rid of that little I. Yeah. Let's expand it, because by Euler formula we can expand it, right? Yeah. C times cosine omega x plus I times C cosine omega x. Yeah. That's by Euler's formula. Yeah. Y2, also Euler formula, only difference is change plus to minus. Now, can we get rid of I in an easy way? I, yeah. Two solutions adding together, is it new solution? Is it solution? This is a homogeneous equation. We have two solutions. Then we add two solutions. Is it another solution? It's also a solution, right? It's called a linearity principle, or super what? Position principle. Superposition principle. Yeah. Yeah. So we add them up. We get solution 2C, but C is 2C. We just use C. Yeah. Because constant scale not important, right? Yeah. In our solution, constant multiple, that constant is not important. So that too is not important. Yeah. If we need, we can multiply any constant, right? Yeah, it's not important. So we drop that too. Okay? So we get C omega cosine omega x. How about we do subtraction of these two solutions? It's also a solution, right? Subtraction. Linearity principle also. Yeah. If you do subtraction, cosine term cancel out. This I term, you have 2I C times. Can you eliminate that 2I? It's constant. Right? It's a constant. Constant is not important, because we can multiply any constant if we like. Okay? So we remove that 2I. Then only sine, C sine left. So this C, because C I represent the E part. So now I go back to this representation. I have cosine and sine. And you do not see I. For case 3, although we need to use complex roots, but in the final solution, two final solutions, we do not need to use I. Is that good? So here you can see we treat complex numbers as our tool. It's a tool. We just use it. Our final product, there is no I. Because our customers, they do not like to see I there, right? Yeah. When you deliver your final solutions, you don't want to show I in your final solutions. Okay? Yeah. Yeah. But the intermediate steps, we need to use I. Okay? Because very convenient. In math operations, it's convenient. Yeah. How about this method? Yeah. Try to get used to it. Yeah. Do not avoid complex numbers. Yeah. As a tool, yeah, we need this tool. Yeah. All right? Yeah. Okay. Yeah. So we find a solution. Yeah. Here we find a solution. Yeah. All right. Yeah. Okay. Yeah. So we finish part A. Yeah. Part A of module 2. Yeah. So we still have 15 minutes. Yeah. Let me talk about one topic in part B. Yeah. Part B. Yeah. Just one topic. All right. All right. Yeah, part B, our second topic. Yeah. Yeah. Existence and uniqueness of solutions. Yeah. B.1, Euler-Cauchy equations. Yeah. A special second-order linear ODE. Yeah. So we call it Euler-Cauchy equations. Yeah. All right. Let's take a look how to solve the form of Euler-Cauchy equations. Yeah. Basic form. This one. Yeah. X squared y double prime plus a, yeah, a constant, but a times x times y prime times by equals 0. Homogeneous. Okay, yeah, here. All right. It's not a standard form. Yeah. Although it's not a standard form. So you can write it standard form, but because for this equation there is a special technique. Yeah. So we don't want to write standard form. Yeah. Yeah. There is a special technique similar to the way we solve, there is one we learned before, Bernoulli equation. Do you still remember Bernoulli equation? Yeah? How did we solve the Bernoulli equation? Bernoulli equation. Yes. That substitution, very special, right? Think about it. That substitution is very special. Here, we also will rely on a special substitution. Bernoulli equation, yeah. Yeah. Substitution, yeah. Here, this one, yeah. It's pretty natural substitution, yeah, but you need to discover it. Yeah. So let me show you the special substitution here. Okay? All right. Let y equals x to the nth power. This form. Okay? Yeah. Yeah. You need to have very good imagination to get this substitution. Yeah? Because, not easy. Yeah. 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 So we can guess, Euler or Cauchy, so they both discovered this substitution. Yeah. Yeah. Then you take first derivative, second derivative. Yeah, it's easy, right? Yeah. By the power rule of derivative. Power rule, derivative. Yeah. Now you can see, now you understand why the substitution is important. Yeah. Here, m is not necessary integer, okay? M just a parameter. M is a parameter, okay? Yeah. Do not assume, because many times when people see m and n, it's very likely people assume integers, right? M and k, yeah. Well, but in this class, our k not integer. Yeah. Most of the time, not integer. Yeah. All right. Now, so let's go back to the original equation. Yeah. After simplification, we factor x to the m out. Yeah. Yeah. So here you can see similar to our previous method, right? Yeah. Our previous method, lambda. We use lambda. Okay? Yeah. Here, it's different. X to the nth power. The previous one, e to some lambda, some power, lambda x power. Okay? Yeah. E to that. Here, if we consider non-trivial, yeah, if we, x cannot be 0, here, yeah. If x is 0, it's a trivial solution, right? So you can consider, trivial solution. So here we assume x not 0, so we can remove the x to the n. Yeah. Remove it. So we get a quadratic equation, algebraic auxiliary equation. It's a quadratic equation. Yeah. Similar to our lambda case, yeah, but slightly different. A minus 1 here. Yeah. Equation A minus in this coefficient. Yeah. Then we apply quadratic formula, write m expressions, m1, m2 this time. m1, m2 this time. Okay? Yeah. All right. Then discussion, 3 cases for the expression under root, right? 3 cases. So you can see, yeah, we can do in some analogous way, right? Yeah, yeah. All right. First, 2 distinct real roots. Yeah. All right. The simplest, m1, m2, you have m1, m2, so you write y1, y2 immediately. y1 equals x to the m1. Yeah. y2 equals x to the m2. That's the final solution. All right. Yeah. Similar to our previous situation. Yeah. Now, double root case. Real double root equals 0. Equal case here. Yeah. The first, this time m, because the root part is 0, so m equals 1/2 times 1 minus a. The first y1 is easy. Yeah, m, x to the m. How about y2? Can you guess? Yeah, because we already have the experience from previous. Can you guess what should we put for y2? What special term? Yeah. Previous one, we put a special term there, right? How about this case here? Let me do some analogy, because here our logical reasoning based on analogy, right? Yeah. Let's do the analogy, so let you see something better. All right. Our previous case, we use the E function structure, right? E function. And here, we use the X function structure, X to something, okay? X structure, all right. Then, in the E function case, we put an extra term, X here, and here, what should we put here? Oh, here, degree, all right, yeah. So here, let me just give you more information. E has much higher order than X, right? Yeah, exponential function increasing much faster than that linear function. Yeah. So E function here, X, all right. There, we lower the order from E function to X. Then here, we also need to lower the order from X to some lower order function. Lower, okay? Hard to see, right? Hard. Yeah, let's guess. Yeah. When we make a guess, we want to make it very natural. The natural log. So here, think about how do we get from e to the x to x? Take a natural log, right? From e to the x to x, you take a natural log. There, from x to some new function, can we take a natural log? Right? This kind of natural analogy. Yes, this natural analogy. Yeah. Let me write it out. Natural log. Yeah? All right. So there you can write y2 function. X to the m times natural log of x. Yeah. How about that? Yeah. Although you can verify. If you like, you can verify easily. Okay? Yeah. All right. Then, case 3. Remember the complex case. 2 complex roots. Yeah. All right. Less than b, we introduce omega, remember? Yeah. Because it's too complicated. We introduce omega. All right. Yeah. So omega, let me put here. The representation of omega here. Okay? Omega. All right. Then, our expression, we can use omega, yeah. Y star version, yeah. Star version because that's not our final version. Our final version, I need to remove that star, okay? So our star version we treat as intermediate version of solutions because we have I there. Yeah, we don't want to see I in our final solution, okay? Yeah, so we write this one. All right. Then Y2 star intermediate version as that, okay? All right. Now, can you see our final version quickly based on the Euler formula? Yeah, this one should not be that hard, okay? Yeah, just replace E function by cosine and sine. Cosine and sine, okay? All right. Yeah. Y1 equals, yeah, look at that, okay? X to the m, cosine parenthesis omega times natural log of x. Natural log of x. Yeah. Look at exponent. We need to preserve the structure in the exponent, okay? Omega natural log of x. All right. Y2 sine. Yeah, sine. Yeah, replace cosine by sine. Y2. Yeah. That's the final solution. Yeah. I is gone. Okay? Complex I is gone. Yeah. Yeah. But we need to use I to do our thinking, right? Yeah. In our logical reasoning, we need to use I. Okay? Otherwise, you need to make a big jump, right? How can you make that big jump? It's hard. Nobody can do that. Yeah. Yeah. All right, so that's it.